So this talk on a thing I called Secret Handshake. So it's a malware command and control channel that uses X509 certs. Sorry. X509 certs as kind of like the data pipeline. There's a little bit of graphics in there, and these are generated with Stable Diffusion, where I just said like secret handshake, cyber, hackers, and this is what it came up with. All right, so my name's John Conwell. I'm a data scientist by trade, been doing that for about 12 years. About 6 years ago, I sub-specialized in InfoSec, specifically looking for threat actor infrastructure, phishing, malware, fraud, that kind of stuff. And at my last two companies, I had like a 6-month project and a 9-month project where they wanted me to just focus on X509 certs. So like the first place, they scrape all the metadata of pretty much every known domain out there. There's like 350 million domains registered. And one day they just added a cert scraper and then said, hey, data scientists, here's 300 million X509 certs, go find bad stuff. So I start parsing them and looking for anomalies and doing weird stuff and like trying to find anything malicious. I found weird things and lots of certs that don't work. But I never found anything malicious, like nothing exciting, right? So my last company was an NDR, and they did the same thing. They're like, we want you to create a model to predict malware. Like it's malware C2 based on the certs. So I pulled on a big data set and also did a phishing one. You know, like when it comes down to it, I didn't find anything. Like, so when it comes down to it, threat actors use certs the same reason we do, to encrypt stuff. Right? There was nothing really, really exciting about how they use X509 certs. But I kept looking, like I wanted to find something really interesting. And I'd heard rumors on Twitter, like red teamers kind of maybe put a script in there, or, putting, modifying the cert, or basically just creating a PEM file, which is a base64 encoded file, calling it a cert, but with, a binary in there. Just doing some interesting things. But for me, the holy grail, both good and bad, right, would be a malware C2 channel that used certs. Searched, never found one, so I was like, well, let's just write one. I'm a blue teamer, but I like to create stuff to understand stuff. So just level set, if you know what malware command and control is, I just want to kind of get everyone up to speed. So stay with me. All right, so malware command and control is basically the communication between the command server and infected clients, right? So the server sends commands to the client runs it, gets the output, and sends the output back to the the server. There's beaconing, which is infected client just saying, hey, I'm here, I'm here, I'm here, when the server's not up and running or doesn't want to interact yet. Servers can download malicious binaries to the client, and vice versa. The infected client can exfiltrate customer data to the command and control server. That's bad. One of the main goals in C2 communication is to blend into network the background traffic, right? There's tons of TLS. So you don't want to do something weird, odd, proprietary protocol that's going to stand out. You want to just blend into all the other stuff. In a C2 channel is literally just the protocol we use. So HTTP, believe it or not, is still used a fair bit. HTTPS, DNS, tunneling, UDP, lots of others, and then X509. All right, so we live in an encryption age. TLS is everywhere. Google does this thing where they analyze what percentage of internet traffic is encrypted. So back in 2019, it was at 95%, right? So a lot, and it's been steady since. The past 4 years, it's pretty much right at 95% of all traffic is encrypted, which means, and X509 certs enable encryption, right? It tells you kind of the algorithms and stuff, does the handshake and the encrypt stuff. So there's a lot of X509 certs just flying around the internet, and they're just files, right? They're just a file, base64 encoded. You can put stuff in files. You can do all sorts of malicious things to them, but we kind of trust them because it's the thing that enables encryption, like the good stuff. So our north-south network logs are littered with TLS sessions, littered with X509 certs, and my last company was an NDR, network detection response. And I haven't really seen a lot of NDRs focus on the certs that much. Like, they might pull out the subject and the issuer and the subject alt name just to kind of give you context of like who issued the cert from this domain or whatever, but not really look at it from a detection perspective. And if I'm wrong, let me know. So that kind of worried me. So the potential to use certs is pretty high. Not a lot of NDRs really look at it. So, and one last bit about certs. Certs are issued by a certificate authority. So like there's trusted certs, trusted authorities, VeriSign, Let's Encrypt, the standard ones you would think about. But you can basically issue your own root cert, be your own certificate authority, and issue your own certs. And that's what this does. Like, I don't know if you could actually do this C2 channel with Let's Encrypt. It would be super slow. All right. So this is, you've probably all seen this as TLS, kind of the TLS flow, the handshake. For command and control, malware command and control, you need what's called a request response pattern, right? Server sends a request, the client does a thing, it sends a response. When I was looking at how could I do C2 over X509, it doesn't really work with TLS because the server sends a cert to the client authenticates it, and that's it. Like, there's no way for the client to kind of send stuff back. So that's not going to work for us. There's a thing called mutual TLS, where the client has a cert also, and the server sends cert down to the client authenticates it, yay. The client sends its cert to the server, and it makes sure it's trusted, and then they can do encrypted communication, which is perfect for enabling that request response pattern. All right, so mutual TLS works great for us. We got that request response channel. The challenges then are going to be how do we embed payloads, data, into X509 certs, and design this request response communication pattern. Kind of looks like you could, because they go both ways, but it's a little harder than that. I'll talk to you about it why. You also have to dynamically issue new certs like every handshake. So if the server says, hey, run who am I? The client's going to run who am I. It doesn't already have that who am I cert, like the answer. So it's going to have to run it, generate the cert, embed the command, then embed the output and send it back, which means network sockets have to be created on both sides every handshake. Like that, to tear down the socket, create a new socket, and go. All right. So for embedding data in certs, this is the CypherCon cert, just for example. I played around, like issuer, you really can't use as a field because it's set by the signing cert, right? So for this one, Let's Encrypt. The algorithm fields, you might be able to change programmatically, but the goal is to have a valid TLS session. And so if you start messing with those, it's not going to work. This serial number is 20 bytes. You can put anything you want in there, up to 20 bytes, but that's a pretty limited payload. It's hex, so it's like you can't do much with it. There's the subject and subject alt name, which corporations actually use, like enterprise services use the subject a lot. They put all sorts of weird stuff into the subject of a cert, but it's pretty obvious. Like if you're, as a defender, looking at certs and like looking for any kind of outlier, it's going to be very, very obvious because most NDRs pull out subject alt name. But that leaves all the other extensions, and there's dozens and dozens of other extensions that are out there, right? And you can use those. So X509 certs are created using what's called ASN1 encoding, which is Abstract Syntax Notation 1. Just a way to create fields, basics for encoding. Every extension has a very, very specific formatting for it, right? So if you want to basically extend an extension, you have to know like which field in which place you want to inject a string or something. Every format has an associated OID, which is object identifier, and that's how like your browser knows to, like it gets an extension, subject alt name, looks at the OID, says, oh, I know this OID. This is how I parse it. And let's see. And a weird one, this is fun. AS1 has a null field. So all AS1 fields have basically the type of the field, string, int, float, null, the value, and the length. So if it's string, you put like dog in there in the value, and the length would be 3. Null actually has value, which should be null, and the length, which should be 0, but you can put anything you want in there, just as long as you set the right length, and the parser is going to go and say, hey, this is null field that's 500 characters long, just goes ahead and then starts parsing along. And so you can actually embed a null field in there, and it'll ignore it. But if your parser pulls it out, then you have a way to send data. So there's a couple extensions I played around with. The NS comment is the one one of the ones I picked for embedding data. NS is Netscape comment. It's a deprecated extension, but you still see it sometimes. So like, it's not too much of an outlier. And you can create what's called an arbitrary extension, which is just an extension that's not has no OID, or the OID is not known, right? So the parser is going to look at the OID, see if it can format or parse it. Can't, skip it. But as long as you know how to parse it, you can. So I use NS comment for the command, and the server. So the client has 2 commands: a beacon, like I'm here, and then response, which is like the response to a bash command. And the server can send sleep, bash, data exfil, or kill. And then I used an arbitrary extension as the payload. So if the server sends a bash, the payload would actually be like, who am I? Just the command to run. And then the client's payload would be John, right? Just whatever the output of who am I is. Let's see. The payload's also used if you're going to do data exfiltration. That would be like the chunk of the file you're trying to exfiltrate, or for a binary dropper, you'd put it in there. In the OID I just picked some random OID, and then just added .666 at the end, and now it's my OID. All right, so we know how to put, this is all done in Python, by the way, so Python is kind of, the cryptography library is what I use to create certs and add payloads into it. So we can create certs with payloads, but we still have to do this command and control kind of communication pattern. It looks, like I said, it looks like you can go, like server sends the thing down, the client sends the thing back, so that's response, reply. But when you create a socket, you have to basically configure it with the cert you're going to use. So before you get the server cert, the client already has to have a cert ready, and they create a connection, exchange certs. So it actually takes 2 mutual TLS handshakes to do the request, and then tear down the sockets, create new sockets, response. So it's kind of like this weird half duplex transition mode. Half duplexes, data goes one way per connection. You have to kill a connection, create a new connection to send back. So what this looks like, real quick, both client server generates the certs. They're going to create their sockets with the certs that they're going to pass. And on this one, like the client is the beacon cert, like, hey, I'm here, and the server is going to be the command, like run ls. So let's see, yeah. Establish connection, exchange, close the sockets. The client is going to parse the cert. It's going to pull out the command. It's going to be, hey, ls. I'm going to run that, get the command, the list directory listing. Now it's going to generate its own cert, embedding that output into it. The server is going to create a sleep, basically. It's like, hey, call back in so many seconds. Create sockets, handshake, exchange. Client gets the server cert, pulls out the sleep, falls asleep. The server is going to pull out the command cert, or the output cert, parse the output, write it to a log, show it in a session if it was live, whatever, and the client goes to sleep. So that's kind of, you see the two handshakes that have to happen in order for that full kind of request reply pattern All right, so here is a demo. See if I can just run it. Ha. All right, so on the first one, what I am showing, there's a server out directory on the right, and that's basically just, let's see, pause. Ha. That's basically showing you that the server out directory is empty. I'm going to do data exfiltration, so proving now nothing there. All right, so I'm going to kick up the Python client, and one thing it's going to show, I don't know if you can even read this because it's so tiny probably, but it's beaconing right now. It's basically saying, hey, beacon, connection's not there, so it just tries again in a few seconds. I'm going to spin up the server and say, pick bash. Bash is going to be the command, and pwd. What directory am I in? To generate the certs, exchange. The client generated its certs, did another exchange, and that's the output. So, whatever that directory is. So now I want to see ls. What's in this directory? Exchange certs, and we have a folder listing, super valuable files. That looks really fun. So we're going to let's look inside super valuable files. And we see hacker extra large. Let's look at that. So I'm going to do data exfiltration on hacker extra large. And so exfil command, and wait for it. Okay. So now I'm basically exporting 6 meg. I'm exfiltrating 6 meg file. But you can't really make, well, you can make a 6 meg cert. You can make it. OpenSSL won't parse it. It'll throw exception. Anything over like 64 meg or 64K, I think, is the biggest cert you can do. So partitioning the file into these little bits, and you can see it creates a lot of certificates. So it's just hammering certs, handshakes, going like crazy. So this would obviously be from a detection perspective, a good signal, right? Big certs, lots of them. And then I send a kill command. The client killed itself. And then I'm going to prove, server out, hey, there's a file. We're going to open it. And, ooh, data breach. See what I did there? All right. Oh, no, not again. There we go. Okay, so that's pretty much the C2 channel, X509 certs. We can talk back and forth, get output, data exfiltrate. I'm a defender, blue team myself, so I never want to release something that could be malicious without providing, how would you detect this? How would you look for this? So this is now the blue team side of things. These certs are not issued by a certificate authority. So like you saw how I had to create this arbitrary extension with like my own custom byte package. I don't know if you could like go to Let's Encrypt and say, hey, create a cert for me, but add these bytes as, with this OID into this cert. So none of them are trusted, issued by trusted authorities. There's going to be a lot of mutual TLS sessions between the same source destination IP and port. Port could change, like you could put that into the communication where it changes port, but same IPs, which would be weird. And they're going to be in close proximity, time proximity, right? It's going to be every couple, 5 seconds, 10 seconds, whatever you want if it's a live interaction session, you don't want to wait an hour per command, right? So it's going to be every 5 seconds, 10 seconds. And it's going to have that kind of same sleep jitter periodicity that you would see with like Cobalt Strike. If you were doing a TLS communication with Cobalt Strike, say you give it like 100-second sleep with a 10-second jitter, it's between 90 and 110 seconds is going to be, the communication. So you look for that periodicity. Same thing here. The big one here, the cert fingerprints will be different. On most of these should be different, right? Because you're creating certs on the fly. They can have different timestamps, different payloads. So 2 different, same IPs talking a lot, different certs. That would be really, really weird. That would stand out. And your byte sizes of the certs are going to be different, right? So small ones for commands, medium ones for like command replies, and bigger ones for data exfiltration. So like it seems like pretty easy set of detection. So when I first did this, I worked at an NDR. So I turned this into the query and ran it, and like I expected one of two things. One is nothing. Like I expected like I would see no traffic that looks like this. The other one, which I kind of wanted but really didn't want, was to find, like, I found the next SolarWinds, like somebody's using this in the wild, and I searched for it, and I never found it, I wrote it, and now, like, somebody's doing this. I didn't find that either. What I found was the third option was there's actually enterprise services that have this mutual TLS traffic pattern, which freaking blew me away. Like, when I first ran it, I saw, like, oh, I've got a lot of traffic, and I looked and I'm like, wait, Titanium and Microsoft and Palo Alto Networks and Cohesity, like these are big names, EMC. And so if anyone knows why, so if you work at any of these companies or admin these services that do mutual TLS with different certs really fast, I will buy you a beer if you come talk to me later, because I want to know. From looking at the certs, the issuer was those companies. The subject, the main thing you usually see is like, I think there's like asset management system. So like the subject had a key value pair and they're like asset ID equals GUID or machine ID or user ID, like some kind of ID and then some kind of alphanumeric value. So these things, the easy way to look for this though is that they repeat, like every hour or every so many minutes. The same set of certs kind of repeats through, right? You might get a new asset, so like you're going to get a new cert shows up, or an asset goes away, so one less cert. But basically, you're going to get the same thing. So it should stand out from what like the C2 traffic would look like. And I didn't check when I was there. I didn't look. I didn't think to look. But the server cert should also be the same every time. Like if the client's basically passing all these new certs over, there's no reason for the server to be creating its own new cert each time. It's probably the same thing. So that would be how you differentiate like these enterprise products from some goofy C2 channel. Mitigation-wise, when I first wrote this, I was like, oh, this is terrible. Like I thought I created something horrible. And then I was thinking about it more, and it's actually super easy to mitigate. Like SSL inspection should, hypothetically, just completely block this, right? Because you're going to basically, the client's going to talk to the inspection server. It's going to create its own TLS session, completely isolated from the inspection server talking to the C2 server, right? So it's not going to pull out like the server, inspection server is not going to pull out like my arbitrary extension and generate a cert to talk to the C2 server and put it back in. It's not going to do that, right? So this theoretically should just, oh my gosh, I blew through that. This should just completely block this type of C2 channel. So one last thing, when I first did this, when I kind of got it done, I was like, oh, it's kind of brittle, right? It creates a lot of artifacts on the hard drive because it has to create all these certs. It's new session every time, killing network sockets and bring them up, tear them down. So it's pretty brittle. What's the next step? Like, is there a way to do it with TLS, but not X509? And I started kicking around ideas. And at the same time, some dude reached out to me on Twitter, and he had the same ideas. And he's like, so we started talking. And the thought is, with just the TLS handshake itself, no certs, like normal, regular cert, let's encrypt. But so random bytes, every TLS handshake, the client and the server create 32 bytes of random bytes. That way, like, they create it, they send it to each other. That way, they encrypt it, send it back, decrypt it, and they can say, hey, we can talk to each other in encrypted land. So we have 32 bytes there. The message ID, the client's supposed to create one, send it to the server. The server is supposed to send the same ID back, but it's deprecated. So like, I don't know, sure the server could probably send a different message ID back and it'd be okay. So now you have 64 bytes of data that you could actually exchange over TLS. If you looked at ESNI, is almost 66 kilobytes of data, which is more than the X509 cert could actually pass in one shot. So now we have 66 kilobytes of data that you could theoretically pass from the client to the server and 64 bytes from the server back, which could be used for an actual C2 channel. The only downsides is, I mean, this would literally be a custom library. You couldn't do it with OpenSSL because you have to like pull out these bits, append them together to get your full package, right? So you gotta come up with a custom TLS library and install it on the client. So the client already has to be infected to do this. So it's gonna be super chatty because lots of TLS sessions, again, same with the mutual TLS, right? It's gonna sit there and hammer these because the data is over the handshake, not the application data. And the other thing is, and when I first thought about this, this one was scary to me as well, because like NDRs don't even look inside like this piece of the TLS handshake. Most NDRs don't look at that. If you had Saracata, you could probably pull those out, right? But SSL inspection, again, would totally block this because, like, say we used the random bytes. The inspection server is not going to take the random bytes of the client, pull it out, create a cert, or pull it out, and with its session to the C2 server, like use those same random bytes. It's just going to create an independent handshake. So pretty sure SSL inspection also would totally block this one, hands down. And that is all I have. One little bit, there's prior art notice on this. About 2 months after I wrote this, this C2 server, or the C2 channel, I randomly ran across a white paper by a dude named Jason Reeves, who invented it like 3 years prior to me. 2019, he wrote a white paper on this, so that's the link. And he also did a TLS binary dropper in Go that does a similar kind of thing. But yeah, there you go. Any questions? Yes. Right. So the question is if it's basically some kind of medical domain or PII kind of protected thing where you're not able to do inspection, well, so inspection is for mitigation. You could still detect this, I think, pretty easily if you had an NDR, something that allows you to kind of query against the aggregate set of fields in all the certs you're seeing. And this GitHub has all the detection logic, or is all written up on the README of the GitHub link. So, yep. What's that? Oh, I don't think it matters, right? So like, if you're using TLS Handshake to pass like the C2 channel, do you really care if it's all that secure? Because you're doing the malicious thing, and you're hiding it in a pretty unique way. Could be secure. I don't really think it matters that much. Like, so another weird one was this. So when I first did the data exfiltration, I was using RSA private key site like 4096. I want to be super secure, but it was slow as shit. Like, it was literally like 1 megabyte every like 20 seconds. It was terrible. And so I realized, like, as I get a smaller private key size, it runs faster because it's smaller key. And so I'm like, well, it's less secure. I'm like, I don't really care, really. That's the smallest I can get. So I got like 1.5 megabyte per second throughput on the same metal. So that's like just compute time. But yeah. Yep. This would be, if like, you wouldn't use this to one of the things what I wanted to do is prove like a C2 channel is possible. I didn't want to create like the most robust malware library there is. So you could have multiple sessions, like multiple affected clients talking to the same server, using like subdomains. So then you would have like different subdomains spinning up its own connections. But you wouldn't be like controlling a big botnet with this. This is more, I would say, very, very targeted. You've done infiltration, and you want to get command and control, within some corporation, right? Very, very targeted, small. Any other questions? Nope. Oh, yep. No, I didn't. You're talking about like registering the OID? Yep. Well, so the OID I picked is the FSB's OID, and then I didn't want to mess with that. But I just added 666 at the end of it. So no, I didn't and the other thing is like the format could change. So it's registered. If I wanted to change format, I'd have to do that. Anything else? Cool. So one last bit, I used Stable Diffusion to create some of the art. So when I was playing around with what does a secret handshake look like in cyberpunk, hacker kind of way, these are the things that came up with. Though there was a couple super uncomfortable ones. I love the one on the left where the computer is caressing the programmer's hands, or just this. So secret handshakes. All right, thanks guys.